Okay. So what we're going to do is the reaction is going to be, I think it's blue dye, blue number 2, I think, that's the way it's recorded. Blue number 2. The method is set up so that you can do blue and red dyes. These are food colors. I think it's blue number 2. Yeah, no, it's blue, blue number 1, excuse me. Blue number 1. Yeah. And we're going to combine this with bleach, sodium hypochlorite, and it doesn't matter what it produces, but it decolors. And what we're going to do is watch this at, where's the wavelength? It's in your method. 630, I think, nanometers. Well, something's up here. Did I put it in your copy? I think it's 630 nanometers. We're going to watch the absorbance. The absorbance units. So you get some kind of units up here and they'll gradually decrease over time. That's going to be a measure of the concentration of blue number 1 as it disappears. Okay. And we're going to do that for full strength and then for half strength. Sodium hypochlorite. Okay. The reason that we have to do it this way is that the concentrations here are so high that we can essentially ignore the concentration of sodium hypochlorite. Remember, we have said that the rate is equal to some K times the absorbance of the blue color. This is only valid, and whatever that value is, this is only valid if the sodium hypochlorite doesn't change. If it changes, then we have to account for that. So actually it's, I'm gonna leave that there. This is the blue dye, and this is the sodium hypochlorite concentration. Okay, if this is high enough concentration that it essentially doesn't change during the reaction, then we combine this one with that one. And now we have an intermediate rate law. That does that. Now we can work, because all we need to do is find out what is this. Is it 0 order, 1st order, 2nd order? And we know how to do that. And we're going to set this up so that it works. So we do it for both concentrations. And then we do that initial rates ratioing to find out what this actually is. Okay. That's the overview of where we're headed. But as far as the data collection goes, you only need to do one series, time series, reading the absorbance over time, so many seconds, take another reading, and then do it for half strength, do it again. That's your data set. What you have to do is find out how much of this do you add to get discoloration over a reasonable amount of time. So that's the first step. And then we have to calculate, we're going to use absorbance units for the blue dye. That's our measure of concentration. But we actually have to calculate the concentration of sodium hypochlorite that's in the reaction vessel. Okay, and I think I've got an example in the handout I gave you, don't I? That's the wrong column. Or did I give you more than one handout? I think I did. Here we go. Yeah, this one right here. Let me show it to the viewing audience. This one looks like that. You don't have a copy of that? Oh, I didn't give you a copy. Okay, hold on a second. And there's another one here. Like that. Oh, and then that one. Oh, it needs to be taller. Let me see if I got it. I should have brought those with me. Kinetics. Here we go. That one. And there we are. Now it's complete. So the one that looks like a spreadsheet is where we calculate the actual concentration of bleach in the reaction mixture. And once you calculate it for full strength, you just take half of that for the half strength. Now, the one key to getting this transition right is this is a certain concentration of sodium and hypochlorite ions in solution. So you've got to match the ionic strength for this one. That's why when we cut this one in half for this experiment, we make up the difference with an equal amount of sodium chloride at that concentration. And I've already made up the solution. So all you have to do is, once you find out how much of this to put in the reaction vessel, you put half of it in there for this one, and the other half you make up with sodium chloride. And that matches the ionic strength. Okay. How much more do I need to say about this? You know what absorbance is? Absorbance, Beer's law. Ever heard of Beer's law? Okay. Beer's law simply says, well, it's got three factors. The concentration of some molecule in solution can be determined by, let's see, an absorptivity constant. I want to use the right lettering here. Where is it? Where did it go? No, it's not that. It must be in my copy. Here we go. So let me flip through all the pages. All right, here we go. Beer-Lambert law. So it's not concentration, it's the absorption. Is based upon the molar absorptivity and the path length and the concentration. So here's the concentration of whatever, they call it chromophore, whatever absorbs the light. This is the path length, and this is the molar absorptivity. But as a practical matter, if you have concentration here, as the concentration goes up, the absorbance goes up linearly. So that's why we can use absorbance instead of concentration, actual concentration values for our calculation. We're going to use absorbance. It's easier to measure. There's another one called transmittance, and absorbance is just the log of the inverse of transmittance. Transmittance is not linear. Absorbance is linear. So that's why we use it. And the meter spits it out for you. It gives you an absorbance value. Okay. There are some, let's see, there's some pre-lab. Those are post-labs. Let's see, is there any yeah, there are some pre-lab questions. Okay, let's take a look at those. Yeah, we may not get done before 4 if I keep talking. So, pre-lab questions. Let me see. There we go. Pre-lab 1. A container of household bleach has 5% sodium hypochlorite. 5% sodium hypochlorite. If the density of the bleach is 1.08 grams per milliliter, 1.08 grams per milliliter equals the density. Calculate the molarity of the solution. Okay. In order to do this, you have to know, what does that mean? Percent. Remember, percent is a dimensionless number. So, here we go. They're saying percent is by mass. So this is 5 grams per 100 grams of solution. But the solution is this value. So if we say we're starting from here, grams per 100 grams of solution. In order to give you concentration in molarity, right? Is that what it asks for? Yeah. We also need to know the molar mass of sodium hypochlorite. So we got to add sodium, oxygen, and chlorine. Sodium is 23, oxygen is 16, and chlorine is 35.45. So it's 74.45. Grams per mole. Okay, so if this is, that's the percent composition of sodium hypochlorite, we need to get it in molar form, moles per liter. So which one do we do first? Well, we can use this one. This is grams of solution per milliliter of solution. So this is going to be 1.08 grams of solution. Cancel those per milliliter. Now we've got it grams per milliliter. Now we need to change grams to moles. So we need grams on the bottom, moles on the top. So that's 74.45 there. And we got milliliters here. We need to get rid of milliliters to make it liters. So that's 1,000 milliliters per liter. And that should be the molarity of the bleach, if it is, in fact, 5%. So let's say 5 divided by 100 times 1.08 divided by 74.45 and times 1,000 is 0.725 molar. Okay. All right. How many grams per liter of sodium chloride are required in order to prepare a solution with a concentration equivalent to the solution in question 1? So if we want that concentration to be reproduced in our sodium chloride additive, then we need 0.725 moles of sodium chloride per liter. And then the question says, how many grams of sodium chloride per liter do we need? So we've got the volume already. We just need to convert moles to grams. So sodium chloride would be 23 plus 3545. $58.45. Okay, let's see. Here. 42.4 grams of sodium chloride per liter will give us this molar concentration. So that way, if we were using pure bleach of 5% concentration, then we would use this sodium chloride solution to in equal volumes to match it. And is that the last one? 3? Okay. Percent of sodium hypochlorite by weight for a liter of bleach that is 0.8 molar and has a density of 1.09. So that's actually taking this one going backwards. 0.8 molar. 0.8 molar would be moles of sodium hypochlorite per liter. And we want it in percent. So we need to change it to milliliters. Right, because the density is going to be 1.09 grams per milliliter. And this is liters 10 to the third. And that gets rid of that one. Now we need to change this to grams. So moles on the bottom, grams on the top would be 74.45. Okay. So that's grams of sodium hypochlorite per milliliter. But we need grams, not milliliters. So 1.09 grams per milliliter. There we go. But that's only 1 gram. So we need 100 grams. There we go. So that should give us the right answer. Times and then 1.09. So 5.46%. Let me see. Cheat sheet here. Let's see if that's right. That was post labs, pre labs. Here we go. 5.5.